We have spoken about conservation of energy, and we noted that energy is not conserved if there are non-conservative forces like friction doing work. So you might want to know, how can we handle friction in the conservation of energy context? In fact, how can we handle dissipative forces in general, such as friction? Well, you might think it means energy is not conserved, and from one perspective, that is true. It is a non-conservative force doing work. But from another perspective, energy is conserved. How is that the case? Let's see. First, let's write the work-energy theorem for a scenario where we have friction and a whole bunch of non-conservative forces acting on an object as it slides along. So we can split that work into the work done by friction and the work done by the other non-conservative forces. The work done by friction will just be this term right here, where Fk is the kinetic friction force and d is the distance that the object slides. We assume that the kinetic friction force is constant, as we usually do, and it is negative because the force of friction is going in the opposite direction that the object slides. Then, of course, we can set all this equal to the change in kinetic energy plus change in potential energy. That is the change in mechanical energy according to the work-energy theorem. All right, now what we can do is we can take this term and add it to the other side of our equation. When we do that, we get this, where we now have the work done by non-conservative forces on one side of the equation, and we have that work done by friction added to the other side of the equation. This term right here, let's call it delta ETH, where delta ETH is equal to that exactly. That force of friction times the distance that the object slides. What is this delta ETH? This is thermal energy, an energy term. So what do I mean by thermal energy? Consider the following scenario. Suppose we have a block that has some initial velocity and it is sliding on a surface with friction. It is slowing down because of the force of friction, as we see here. What is going on? Well, from one perspective, the force of friction is doing work on our object. So that would be looking at our work-energy theorem like this. But from another perspective, the object and the surface are warming up, right? Just think about rubbing your hands together or rubbing any two objects together. They feel warmer. Their temperature has increased. We call that energy thermal energy. So from another perspective, we can instead think of friction as increasing the thermal energy of our object. And so we have our delta E thermal term on this side, thinking of things from this perspective, where we have the work done by other non-conservative forces will be equal to the change in mechanical energy plus the change in thermal energy because of friction. So let's talk about this thermal energy a little bit. Friction causes the increase of thermal energy of the objects that are rubbing together. This is not just the thermal energy of the block, but the surface it rubs on, because as you know, when two objects rub together, they both get warmer. This means we have an increase of thermal energy of our block and the surface it is sliding on of the two objects that are rubbing together. You should note that this thermal energy term, this delta E thermal, in some books is called internal energy, and you'll see it written like this, delta E internal. And this is because it is the energy of objects warming up. It is the energy of their molecules that make them up, vibrating and moving a little bit faster. So in some sense, it is an internal energy to our objects. Another important note is that technically it is improper to calculate the work done by friction by taking the force and multiplying by the distance. This is because our work equation that we have discussed previously is only true for a point particle, but this object is not a point particle. When you have objects rubbing together, they are not point particles. However, it'll work so long as you are modeling your object as a point particle. So this will be true if you model your object as a point particle, which means in particular, it is true if you're looking at the work done on an object's center of mass. And we'll get into center of mass a little bit later, but it's a way that you can treat an extended object like this as a little point particle at its center. So if you're looking at the work done on the center of mass or looking at the work done on your object treated as a point particle, you may use this to calculate the work done by friction. However, you should also note that it is always proper to find thermal energy as defined like this. So this will always be the thermal energy term, which is the negative of the work done by friction on the center of mass of our object, or on our object treated as a point particle. As I alluded to a little bit before, both the object and the surface warm up together. Because of this delta E thermal term right here, it's just telling you the total increase in thermal energy of both your box and your surface. You can't determine how much of this energy is going into your box or going into your surface. All you know is that this is the total increase of thermal energy of both objects. So that's thermal energy. Now, how does this relate to energy conservation again? Well, remember, from our work energy theorem, we can either think of the work done by friction on the center of mass plus work done by non-conservative forces as change in mechanical energy, or we can think of the work done by non-conservative forces as the change in mechanical energy plus the change in thermal energy. What is the difference between these two equations, aside from having a term on the left-hand side and moving it to the right? Well, the difference is in one case, you're thinking of friction as doing work, and on the other case, you're thinking of friction as increasing energy. What energy? It's the energy of both the block and the surface it is rubbing against. So, if you include both surfaces inside your system, then you will get this kind of equation. You'll have the work done by non-conservative forces on your system. It's change in mechanical energy plus change in thermal energy. This means if the work done by the other non-conservative forces is zero, you will get energy conservation again, simply by including both surfaces that are rubbing together inside the system. So now, when you do energy conservation problems and you have friction, so long as there is no work done by other non-conservative forces, and the only work done is done by friction or other dissipative forces, then you will have change in kinetic energy plus change in potential energy plus change in thermal energy, which for friction is defined as FKD, will be equal to zero. Energy is conserved. Do note, however, that although energy is conserved in this system of both of the objects rubbing together, the mechanical energy, which remember was change in Ke plus change in U, change in kinetic energy plus change in potential energy, is not conserved. This quantity is not conserved because you have this change in E thermal, this change in thermal energy term added to this equation. So your total energy is conserved, but your mechanical energy is not conserved when you include friction in your system.